My name is Aubrey Rach, and this is my Physics 2211 lab number 2, analyzing the motion of a falling object. So to get started, we're going to go to the intro and some helpful concepts to know, and then we'll break down the system and the forces. Then we'll jump into our data comparison, and then look at the code for our computational model, and then we'll tackle some what-if questions at the very end. So in this lab, we compared the motion of a falling object using actual data and that collected from computational models, one assuming no drag and one accounting for it. For actual model, drag was an important factor and could not be considered negligible. And the computational model that did not account for drag produced highly inaccurate results, while the one that did account for drag was fairly precise, as we'll see in a moment. So some concepts that you might need to be familiar with: Newton's second law, the force of gravitational pull on an object that's falling, drag force, where B was the constant of proportionality of the magnitude of drag force, and then the unit vector and direction of velocity in the experiment V hat is equal to J hat. So for our system, we dropped a roughly kite-shaped piece of paper, and the only two forces that were acting in this system that we were assuming is closed were gravity and drag force itself. A question to keep in mind or to address is, as the forces balance, like a drag force and gravity does, net force equals 0. And what is the relationship to terminal velocity within that? Because terminal velocity is defined as when the drag force balances out the force of gravity, there's no longer an acceleration, which would mean net force would be equal to 0 as the object is no longer accelerating. So I guess that answers that. For the model comparisons, we have three sets of data here to compare. We have the tracker software in blue, the computer model that does take on drag as a variable, and then the one that does not. So in blue, the actual data where we dropped the kite-shaped piece of paper is plotted, which we can see lines up nicely with the yellow data that was collected from the computational model that accounted for drag. They are very similar to one another. The red data has no drag, and it saw our piece of paper was predicted to reach the ground much, much sooner, upwards of 3 seconds sooner. And this prediction makes sense, as there would be no drag force to balance out the gravity, and it would continue to accelerate. So the code for the no drag computational model, there was no B necessary, so we just started off with our initial conditions where the paper had a mass of 1.6 grams. It started off 1.63 meters in the air, where up is defined to be the positive y and down is defined to be the negative y. Our delta t was set to 0.033, and we measured from t equals 0 to t equals 0.933, so almost a second. And we see in the bottom some of those physics principles start to be worked out, where in this case we did not have to account for drag, but we did have the force of gravity, and then we had to calculate net force. So for the computational model that does include drag, the only changes that were really made were to calculate B, where we found the surface area of the piece of paper and a couple of other constants to calculate for the proportionality constant, and we see that integrated in line 56, where B equals 0.0045. And then those physics principles are, again, being applied down at the bottom, where F net is equal to the force of gravity and the force of drag acting together, and we do have to account for that drag. And then finally, after we've seen the results of this, we've seen that drag plays a really big factor in the objects that you're dropping from a height. We can go into some what-if questions. So what if the object were thrown? So terminal velocity does not change based on the initial velocity of an object. Think of it as like you get like a 10-meter head start in a 100-meter race. Like, you're still going to reach the same top speed. However, it will take you less time to cross the finish line per se. And so another question was, do any of these models predict terminal velocity? So the velocity versus time graph of the computational model that accounted for drag does appear to predict terminal velocity. As we see the velocity begin to plateau at the bottom, it sort of looks like an exponential decay. And this plateauing indicates a cease to acceleration, and it does seem to predict terminal velocity. And lastly, to conclude, I believe that the large surface area of the object caused terminal velocity to be reached very quickly as the drag force balanced out gravity. And basically what all this means is that depending on the objects that you're using, like spheres are clearly very aerodynamic, and drag can almost be assumed to be negligible sometimes. But for objects like pieces of paper, drag is like a resistant force against gravity, and it will definitely change like the results and timetables it will take objects to hit the ground and when they hit what velocity.